Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the heat death, finding stillness in the ultimate horizon. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The concept of heat death arises from the second law of thermodynamics, highlighting the inevitable trend toward increased entropy within closed systems. In this state, energy becomes uniformly distributed, leading to an absence of usable energy for doing work. The gradual cooling of stars and the eventual dimming of cosmic structures contribute to this scenario, where temperatures approach absolute zero. Over vast cosmic timeframes, galaxies will cease their formation, leaving behind a desolate expanse punctuated only by remnants of once vibrant celestial bodies. These remnants include black holes, neutron stars, and cold gas, each a testament to the processes that shaped the universe before its inevitable stillness. The galaxies, now isolated, will drift further apart, their light fading into obscurity. In this quiet expanse, the universe's fate unfolds through the slow decay of matter and the gradual disappearance of energy gradients. The cosmic microwave background radiation, a relic of the early universe, will continue its journey toward uniformity, signaling an end to structure and complexity. The silence of this final stage is not one of chaos, but rather a profound stillness, where all processes cease. This distant future represents a culmination of physical laws, where the universe settles into a state of equilibrium, devoid of change and life, forever drifting in the dark. The foundations of thermodynamics emerged during the 19th century, as scientists began to explore the intricate relationships between heat, energy, and work. Key figures such as Sadi Carnot, who proposed the idealized heat engine, laid the groundwork for understanding energy transfer and efficiency. Subsequent developments by Rudolf Clausius and William Thomson, later known as Lord Kelvin, formalized the laws governing energy conservation and entropy. Their insights revealed that energy conversion processes inevitably lead to an increase in entropy, marking a gradual shift toward disorder. Observations of steam engines and other heat-based systems fueled these theories, highlighting how energy losses limited efficiency and underscored the inevitability of decay. The second law of thermodynamics, asserting that entropy in an isolated system tends to increase over time, painted a stark picture of the universe's fate. The implications extended beyond mechanical systems, suggesting that all processes, including those governing stars and galaxies, are subject to these principles. These initial theories formed the bedrock for further exploration into the cosmos, influencing the understanding of stellar life cycles and the eventual fate of celestial bodies. As these concepts evolved, they illuminated the pathway toward the ultimate horizon, where the universe, having exhausted its energy reserves, would exist in a silent, unchanging state. The quiet realization of this eventuality reflects the profound culmination of scientific inquiry into existence itself. The foundational principles governing energy and matter dictate the behavior of all physical systems, framing the universe within a structured yet inexorable progression. The first law of thermodynamics, the conservation of energy, asserts that energy cannot be created or destroyed, it merely transforms. This principle establishes a baseline for understanding energy exchanges, influencing everything from stellar formation to the decay of radioactive isotopes. Transitioning to the second law, entropy emerges as a central theme. It indicates that in any energy transfer, disorder tends to increase, leading systems toward equilibrium. This natural tendency toward greater disorder informs the fate of all thermodynamic processes. As systems evolve, the available energy for doing work diminishes, guiding them toward increasingly chaotic states. The third law further elaborates on this concept by positing that as temperature approaches absolute zero, the entropy of a perfect crystal approaches a constant minimum. This law implies a limit to how orderly systems can become, reinforcing the inevitability of entropy's ascendancy within the cosmos. Through these laws, a detailed framework emerges, illustrating the inexorable march toward thermodynamic equilibrium. Each interaction, each transformation, and each instance of energy transfer contributes to the gradual approach of this ultimate state of calm, where the universe finds its stillness in the heat death. The entropy principle signifies the inevitable trend toward disorder as systems evolve over time. In this region, the concept manifests through increasingly randomized arrangements of particles, energy dispersing in a quest for equilibrium. This relentless march toward chaos is not merely an observation, but a fundamental characteristic of the universe itself. Within closed systems, energy transitions lead to a gradual increase in entropy, rendering previously organized structures into a formless state. The molecular collisions, electromagnetic interactions, and thermal exchanges all contribute to this expansive disorder. Stars, once vibrant and life-giving, will eventually succumb to this principle, exhausting their fuel and collapsing into remnants that radiate minimal energy. These remnants, composed of black holes and cold stellar corpses, mark a transition not only in physical form, but in the nature of existence itself. Over eons, as energy becomes more evenly distributed, the vibrant phenomena observed in the cosmos will fade into a dim, uniform background. The implications of the entropy principle extend beyond mere physics, touching upon the essence of time and the arrow that defines it. Each moment, each fleeting interaction, incrementally fosters this increase in disorder, leading toward a universe where all distinctions dissolve, leaving a quiet, unyielding expanse. This is the path toward a serene yet desolate conclusion. The second law of thermodynamics indicates that energy spontaneously tends to disperse and spread out. This principle governs the behavior of systems, dictating that in isolated environments, entropy or disorder steadily increases over time. In this context, energy transformations are never 100% efficient, leading to inevitable losses, primarily in the form of heat. It is this relentless march toward disorder that shapes the fate of all matter and energy within the universe. Within these vast expanses, systems such as stars and galaxies expel energy, contributing to the gradual rise of entropy. As stellar processes convert hydrogen into helium, they release immense amounts of energy. Over billions of years, however, these once vibrant entities exhaust their fuel, resulting in a transition to states of greater entropy. The remnants of these celestial giants, whether white dwarfs, neutron stars, or black holes, represent the final chapters in their thermodynamic narratives. The cosmic landscape becomes increasingly homogeneous as energy continues to dissipate. Over eons, even black holes will evaporate, leaving behind a cold, empty universe. This culmination reveals a future devoid of structure and activity, where all matter exists in an equilibrium state. In this ultimate horizon, the last flickers of energy will fade, marking a profound stillness across the cosmos. The universe's expansion is a phenomenon that fundamentally alters the fabric of existence. Stretching across vast distances, galaxies are receding from one another, propelled by an unseen force. This relentless expansion began with the Big Bang, a singular moment that initiated time and space as we understand it. From that point, the cosmos has been in a state of continuous growth, with galaxies moving away at increasing speeds. Observations reveal that this expansion is not uniform. Variations in the rate can be attributed to different densities of matter and energy in various regions. Dark energy, a mysterious force, plays a significant role in driving this acceleration, pushing galaxies further apart. Current models suggest that as time progresses, the distances between celestial bodies will continue to increase, leading to a gradual isolation of galaxies from one another. This relentless movement shapes the fate of the universe. Over cosmic timescales, gravitational forces will struggle against this expansion. Eventually, isolated clusters of galaxies may exist within vast emptiness, their light fading into the cosmic darkness. Even the cosmic microwave background radiation, remnants of the early universe, will diminish in intensity as space continues to stretch. This slow dissolution into stillness reflects not only the current state of the cosmos, but also hints at the eventual fate awaiting all structures within it. An essential remnant of the universe's infancy, cosmic microwave background radiation provides a glimpse into conditions shortly after the Big Bang. This faint glow, permeating all of space, serves as a vital clue to understanding the universe's early moments. Originating from a time when matter and energy coalesced into a uniform hot plasma, it reveals the uniformity that characterized the cosmos at approximately 380,000 years after its inception. The faint echoes of this primordial radiation manifest as a nearly uniform temperature of 2.7 degrees Kelvin. Small fluctuations within this radiation, however, carry significant implications. These temperature variations are indicative of the density fluctuations that would eventually lead to the formation of galaxies, stars, and the intricate structures observed today. Analyzing these fluctuations allows scientists to reconstruct the expansion history of the universe, offering insight into its evolution and the forces at play. As the cosmos continues to expand, this radiation serves as a cosmic background against which all events unfold. It represents a silent witness to the myriad processes shaping the universe, from the formation of celestial bodies to the gradual cooling of interstellar space. The presence of dark energy plays a crucial role in the ongoing expansion of the universe. This mysterious force, which constitutes approximately 70% of the cosmos, drives galaxies apart at an accelerating rate. Observations indicate that it influences the large-scale structure of this vast expanse, contributing to the observed phenomenon known as cosmic acceleration. Dark energy's effects manifest in the behavior of supernovae, whose brightness reveals the distance of their host galaxies. These measurements show that galaxies are receding from one another, not merely influenced by gravitational forces but propelled by an unseen force. The implications of this sustained acceleration extend to the ultimate fate of the universe, suggesting a future characterized by isolation and chilling darkness. In this state, the galaxies will drift further into the void, separated by ever-increasing distances. Stars will eventually exhaust their nuclear fuel, leaving behind cold remnants scattered throughout this expansive realm. The cosmic background radiation, a remnant of the Big Bang, will continue to cool, becoming increasingly faint. This relentless expansion hints at a stark conclusion, a universe steadily approaching a state of entropy where energy becomes uniformly distributed and activity ceases. As the time progresses, the cosmos will transform into a vast empty expanse, a testament to the inexorable march of dark energy and the inevitable decline into stillness. Understanding the Big Bang Theory reveals the extraordinary origins of the universe, where energy condensed into matter, igniting an expansion that continues to this day. This concept posits that approximately 13.8 billion years ago, an infinitely dense point underwent a rapid inflation, giving birth to space and time. Through this process, the fundamental forces emerged, shaping the cosmos as it expanded. The remnants of this explosive event can be observed in the cosmic microwave background radiation, which permeates the universe. This faint afterglow, a remnant of the initial heat, offers a glimpse into the primordial state of existence, revealing the uniformity and slight fluctuations that would eventually lead to the formation of stars and galaxies. The initial moments of this expansion saw quarks, electrons, and other elementary particles emerge, setting the stage for the complex structures that would evolve. As galaxies coalesced under gravitational influence, they formed clumps of matter, evolving into the intricate network observed today. The unfolding narrative of the universe is one of continual transformation, interspersed with epochs of formation and destruction. Understanding this vast chronicle illuminates the delicate balance between expansion and the eventual fate that awaits. In this sweeping journey, the echoes of the Big Bang resonate, a profound reminder of the origins from which all phenomena arise. The life cycle of stars illustrates the intricate processes governing the cosmos. Born from dense clouds of gas and dust, these stellar nurseries ignite through nuclear fusion, transforming hydrogen into helium. This fusion generates immense energy, resulting in the radiant glow that characterizes a star's existence. Over millions to billions of years, they evolve through various stages, each defined by the balance between gravitational forces and the outward pressure of fusion energy. As hydrogen is consumed, the core contracts while the outer layers expand, leading to the formation of red giants. This swelling marks a transition where heavier elements begin to fuse, culminating in a brief yet intense phase of instability. Not all stars will reach the same fate. Those with sufficient mass will undergo supernova events, expelling their outer layers into space. This explosive demise enriches the surrounding interstellar medium with heavier elements, contributing to the birth of new stars and planets. In contrast, smaller stars, like the Sun, gently shed their outer layers, becoming planetary nebulae. The remnants cool and shrink into white dwarfs. Leaving behind the spectral echoes of their former brilliance. In their earlier stages, stars undergo a magnificent transformation, expanding into red giants. These colossal bodies exhibit a radiant glow, fueled by the fusion of helium into heavier elements. As they exhaust their hydrogen supply, the internal pressure diminishes, causing the outer layers to swell dramatically, enveloping nearby planets in a swirling embrace of gas and dust. The transition to a red giant is a precursor to a cataclysmic finale. In some instances, the core continues to collapse, leading to a supernova explosion. This violent event signifies the death throes of massive stars, unleashing an extraordinary amount of energy and ejecting stellar material into space. This process not only disperses elements forged in stellar interiors, but also enriches the surrounding interstellar medium with the building blocks necessary for new star formation. In the quiet aftermath, remnants of the explosion can manifest as pulsars or neutron stars, each a testament to the immense gravitational forces at play. Nearby regions may witness the birth of new stars, ignited by the shockwaves from such explosions. This cycle of creation and destruction continues relentlessly, a fundamental aspect of the universe's ever-evolving narrative. Each phase reflects the intricate balance inherent in stellar evolution, a constant interplay of life and death among the celestial giants. The life cycle of massive stars, black holes, on the other hand, represent a boundary beyond which nothing can escape their grasp. Formed from the remnants of the most massive stars, these regions of spacetime exhibit such strong gravity that even photons are unable to traverse the event horizon. The singularity at the center remains an enigma, where the laws of physics as currently understood cease to apply. These remnants contribute to the cosmic environment in unexpected ways. Neutron stars emit beams of radiation, detectable as pulsars when aligned with Earth. Black holes can influence the motion of nearby stars and gas, often forming accretion disks that emit high-energy radiation as matter spirals inwards. This complex interaction between remnants shapes the surrounding cosmos, continuously redistributing energy and mass throughout the universe. White dwarfs represent the final evolutionary stage of stars that have exhausted their nuclear fuel. These stellar remnants, typically the size of Earth but containing a mass comparable to that of the Sun, possess an extraordinary density. Their remnants emerge after a star expels its outer layers, leaving behind a hot core that begins to cool gradually over billions of years. Initially, they shine brightly due to residual heat, but this luminosity fades as time progresses. In this region of the cosmos, they serve as essential contributors to the galactic environment. The cooling process of white dwarfs plays a role in the thermal history of galaxies. Their energy output, though diminishing, influences the surrounding interstellar medium, contributing to the delicate balance of energy and matter within the galaxy. As they evolve, these stars may interact with companion stars in binary systems. Mass transfer can lead to various phenomena, including novae or type Ia supernovae, which are pivotal in enriching the interstellar medium with heavier elements. The aftermath of these events adds complexity to the cosmic landscape, facilitating the formation of new stars and planetary systems. Through their gradual cooling and eventual fate, white dwarfs embody both the end of stellar life cycles and the continuous transformation of the universe, marking the passage of time in the grand cosmic clock. Clusters and superclusters emerge as vast aggregations of galaxies, shaped by gravitational forces acting over billions of years. These colossal structures form through the gradual amalgamation of individual galaxies, drawn together by the invisible threads of dark matter. It is within these regions that the intricate interplay between gravity and cosmic expansion becomes evident. As galaxies collide and merge, they undergo profound transformations, leading to the birth of new stars and the eventual coalescence of gas and dust into vibrant stellar nurseries. The dynamics within clusters are complex, characterized by interactions between different galaxies, some bustling with the activity of star formation, while others languish in a more quiescent state. In this environment, supermassive black holes often reside at the centers, their immense gravitational pull influencing the motion of surrounding galaxies and gas. As these entities influence their surroundings, they play a critical role in regulating star formation rates, creating an intricate balance that defines the evolutionary paths of the galaxies. Superclusters, the largest structures in the universe, serve as the scaffolding upon which galaxies are anchored. Their sheer scale provides a cosmic framework, with filaments of matter extending across vast distances. This arrangement reveals the underlying structure of the universe, illustrating both its vastness and the interconnectedness of its myriad components. This intricate network, known as the cosmic web, comprises filaments of dark matter and gas, bridging together clusters of galaxies. These filaments form an expansive architecture, revealing the gravitational forces that shape the cosmos. Each node within this structure houses galaxies, their collective mass influencing the paths of light and matter in their vicinity. Observations indicate that the density of matter varies significantly throughout this region, leading to a complex interplay of gravitational attraction and repulsion. Some areas exhibit a density greater than the average, becoming gravitational wells that draw in surrounding matter. Conversely, voids emerge where fewer galaxies reside, creating expansive, almost empty swathes within the grand design. The temperature of intergalactic gas within these filaments can reach millions of degrees, illustrating the energetic processes occurring far beyond the immediate vicinity of individual stars. Hot plasma flows along these threads, while cooler regions allow for the formation of new stars. This dynamic environment facilitates the ongoing evolution of galaxies as they merge and interact across immense distances. Mapping this web provides valuable insights into the universe's expansion. Driven by dark energy, observations from various telescopes continue to refine our understanding of this structure, shedding light on the fundamental nature of existence itself. The cosmic web serves not only as a blueprint of the universe, but also as a reminder of its ever-evolving state. Black holes represent the ultimate gravitational wells within the cosmic fabric, formed from the remnants of massive stars. These entities exhibit a gravitational pull so intense that not even light can escape. The event horizon marks the boundary beyond which no information can return, creating a distinct separation between the observable universe and regions shrouded in darkness. Within this region, matter is compressed to extraordinary densities, generating immense pressure and temperature. Surrounding accretion disks glow brightly as material spirals inward. Heated by friction and gravitational forces, this phenomenon can produce spectacular bursts of energy, radiating across various wavelengths, illuminating the shadowy presence of the black hole. The study of these objects reveals fundamental truths about the nature of gravity and the behavior of matter under extreme conditions. They serve as laboratories for testing theories of physics, particularly the interplay between general relativity and quantum mechanics. These gravitational giants also play a crucial role in the dynamics of galaxies, influencing star formation and galactic evolution. The quiet presence of black holes beckons further inquiry into the very fabric of space and time. As they merge and grow, they reshape their surroundings, continuing to challenge our understanding of the universe. This enigmatic nature invites contemplation on the profound, yet often unobservable aspects of existence. Hawking radiation emerges from the intersection of quantum mechanics and general relativity, offering insights into black hole dynamics. This phenomenon suggests that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. Particles and antiparticles spontaneously form in this region, with one falling into the black hole while the other escapes. The escaping particle manifests as radiation, thus allowing for a gradual loss of mass from the black hole itself. The implications of this radiation extend into the realm of entropy and thermodynamics. Black holes, once thought to be the ultimate traps for information, may actually emit thermal radiation, leading to the eventual evaporation of their mass over astronomical timescales. This process raises questions about the fate of information swallowed by black holes, challenging the conventional understanding of information conservation in physics. As black holes emit Hawking radiation, they become increasingly cold and less massive, eventually leading to their complete disappearance. This gradual transformation highlights the delicate balance between gravitational forces and quantum mechanics. The study of Hawking radiation not only deepens comprehension of black hole behavior, but also serves as a bridge to understanding the broader universe's fate. In this quiet expanse, black holes reside as enigmatic remnants of cosmic evolution, their radiant emissions quietly echoing the mysteries of existence. This region, characterized by its vast emptiness, is intricately woven with dark matter, an invisible form of matter that does not emit light. It interacts primarily through gravitational forces, exerting a profound influence on the formation and structure of galaxies. These unseen entities are responsible for a significant portion of the mass in the universe, shaping the very fabric of cosmic architecture. Galactic clusters, sprawling arrangements of galaxies bound by gravity, exhibit a gravitational pull that exceeds the visible matter present. Observations reveal that the distribution of visible galaxies aligns with the presence of dark matter, indicating that this elusive substance forms a scaffold upon which galaxies coalesce. It permeates this expanse, creating a web-like structure that dictates the motion of celestial bodies. The gravitational lensing effect serves as a vital tool in mapping this hidden component. Light from distant galaxies bends around massive clusters, revealing the presence of dark matter through its effects on light trajectories. This phenomenon provides insight into the density and distribution of dark matter, allowing for a deeper understanding of its role in cosmic evolution. In contemplating the universe's future, the influence of dark matter cannot be understated. It remains a critical component in the ongoing quest to decipher the ultimate fate of cosmic structures, guiding the path toward equilibrium in the vastness of space. The nature of time presents a profound philosophical inquiry, intertwined with the fabric of existence itself. In this context, it is perceived not merely as a sequential progression but as a complex interplay of events and experiences. These moments, often categorized as past, present, and future, reveal a fluidity that challenges rigid definitions. Time, in this view, becomes a dimension in which all occurrences are interconnected, influencing one another through causality. Philosophers have long debated its essence. Some posit that it is an objective measure, a linear pathway leading to inevitable conclusions. Others propose that it is subjective, shaped by consciousness and perception. This duality reflects a rich landscape of interpretations, each contributing to the understanding of existence within the cosmos. The implications of this exploration extend into the realms of physics and cosmology, where time is often treated as a variable. In the context of the heat death, the concept of entropy emerges, suggesting an inevitable drift towards uniformity and stillness. As systems reach thermodynamic equilibrium, the movement and change that characterize existence become a distant memory, leaving behind a void. In this quiet culmination, the philosophical reflections on time serve to deepen our comprehension of the universe's final state, inviting contemplation on existence itself. Time's arrow, defined by the relentless progression towards entropy, illustrates the unidirectional nature of this phenomenon. In every corner of the cosmos, this principle governs the behavior of systems, dictating that complexity will invariably yield to disorder. The gradual disintegration of structured forms into chaos underscores this inevitable march forward, rendering the past a repository of potentialities now spent. Within this framework, the flow of time becomes a tangible experience, Events unfold with a distinct beginning, middle, and end, with each moment irrevocably consumed by the next. It is this linearity that shapes the perception of reality, creating a narrative that is both intimate and expansive. The past echoes faintly through the remnants of what once was, while the future remains an untouched canvas, forever shifting under the weight of current actions. Entropy, as a concept, serves as a gentle reminder of the fragility of organized states. Each particle, each atom, contributes to an overarching trend that favors decay over preservation. The universe, in its vastness, embodies this truth, with galaxies drifting apart, stars burning out, and structures collapsing into themselves. Such observations evoke a sense of tranquility amidst inevitable dissolution, a paradoxical peace found in the understanding that all things eventually return to simplicity. The concept of thermal equilibrium illustrates a state where all temperature gradients cease to exist, resulting in uniform energy distribution throughout a system. In this state, energy flows cease, leading to an absence of significant interactions between particles. The implications extend beyond mere physical principles, touching upon the very fabric of existence. Within this equilibrium, particles exist in a serene dance of minimal activity, each contributing to a collective stillness that defines the essence of the universe. Energy, once vibrant and dynamic, stabilizes into a homogeneous state. This transition reflects the gradual approach toward the ultimate fate of the cosmos. In such a realm, the distinctions between celestial bodies blur, merging the once vibrant stars and planets into a monochromatic existence. The cold remnants of stellar explosions and the whispered echoes of ancient galaxies fade into a dilute background where no significant temperature variance can be detected. This zone of stillness signals the end of cosmic evolution, a final chapter where complexity yields to simplicity. Fluctuations, once a hallmark of vibrant systems, diminish as the universe reaches its terminal phase. Understanding this process provides insight into the natural order, showcasing the inevitability of thermal equilibrium as a defining feature of cosmic destiny. In this quiet resolution, the universe finds peace in its ultimate horizon. The concept of heat death describes a state where the universe reaches maximum entropy, a condition characterized by uniform distribution of energy. This eventual state denotes a profound stillness, where no thermodynamic free energy remains to perform work. All structures, from galaxies to stars, will fade into obscurity, existing only as scattered remnants of their former selves. In this scenario, the temperature of the universe approaches absolute zero, a threshold at which atomic motion ceases. The remnants of all matter will drift into an expansive void, leaving behind a dark, cold expanse devoid of life or light. These conditions signify an irreversible transition, the culmination of cosmic evolution. Stars will exhaust their nuclear fuel, resulting in their transformation into white dwarfs, neutron stars, or black holes. Over eons, gravitational forces will pull these remnants into a state of aggregation. Yet, as cosmic expansion continues, the distances between particles will increase, rendering any interactions increasingly rare. This gradual fading signifies the end of complexity, where structures that once thrived in vibrant states give way to a monotonous equilibrium. The universe, in its final act, embraces an eternal quietude, a resting place for all that once existed. Stars, those luminous beacons that punctuate the cosmos, undergo a gradual decline as they deplete their nuclear fuel. In the later stages of their existence, they transition from vibrant spheres of energy into increasingly dimming entities. This process is marked by a slow but inexorable cooling, as the once fervent fusion reactions that sustain their brilliance begin to falter. In the twilight of their life cycles, many stars expand into red giants. This expansion is accompanied by a profound transformation of their internal dynamics. The core contracts under gravity, intensifying pressure and temperature, while the outer layers swell, becoming tenuous and diffuse. Eventually, these stars expel their outer envelopes, casting off material that may contribute to the formation of new celestial bodies. For smaller stars, this leads to a serene conclusion as they shed their incandescent shells, leaving behind a white dwarf, a remnant that cools over billions of years. Larger stars, when their core collapses, may result in a supernova, an explosive end that temporarily outshines entire galaxies. Yet, even after such cataclysms, the remnants will yield to coldness, drifting into the void. This slow, methodical cooling of stellar remnants contributes to a universe increasingly defined by its stillness, a stark reminder of the impermanence of cosmic phenomena. Energy plays a pivotal role in the sustainability of cosmic structures. The initial burst of stellar formation ignites an intricate process where hydrogen fuses into helium, releasing tremendous amounts of energy that illuminate the surrounding darkness. This energy fuels the growth and evolution of galaxies, nurturing the birth of stars and the formation of planets. As stars age, their energy output wanes. The balance between gravitational collapse and radiation pressure shifts, leading to various stellar life cycles. Red giants and supernovae disperse materials into space, enriching the interstellar medium with heavy elements, which are essential for subsequent generations of stars and planetary systems. This cycle of energy release and material recycling defines the dynamics of this vast expanse. In the aftermath, remnants such as neutron stars and black holes embody concentrated energy reservoirs. Their gravitational pull influences nearby matter, funneling it into accretion disks, where incredible temperatures reignite fusion processes. This continual exchange of energy fosters localized pockets of activity amidst the broader quietude. The eventual fate of the universe, characterized by its gradual descent into equilibrium, hinges upon these intricate interactions of energy. Each transformation contributes to the evolving landscape, underscoring the delicate balance that sustains cosmic existence. Even as entropy inexorably advances toward the ultimate stillness of heat death. Theoretical models of heat death present a profound exploration of the cosmos's final fate, each offering unique perspectives on the mechanisms driving this inevitable conclusion. These frameworks propose that as energy disperses across vast distances, systems reach a state of maximum entropy. In this scenario, temperature gradients diminish, leading to uniformity where energy transactions cease. One prominent model involves the concept of thermodynamic equilibrium, where all forms of energy become uniformly distributed. This state results in a universe devoid of usable energy, rendering processes that sustain life and structure impossible. In such a model, stellar remnants, black holes, and subatomic particles drift aimlessly through an increasingly cold expanse, their interactions diminishing to nearly zero. Another perspective considers the role of dark energy in accelerating the universe's expansion. As galaxies recede from one another, the fabric of space-time stretches, further isolating matter and contributing to the cooling of cosmic environments. The implications of this expansion extend to stellar evolution, leading to the gradual disintegration of celestial bodies. These theoretical frameworks converge upon a singular outcome: a universe that, in its quest for equilibrium, settles into a state of perpetual stillness. The exploration of these models provides insight into the profound transformations that await, illuminating the path toward an unchanging, quiet cosmic future. Statistical mechanics serves as the foundation upon which the concept of entropy is built, elucidating the underlying behavior of particles and their interactions. In this framework, macroscopic properties emerge from the collective actions of countless microscopic entities, each following deterministic laws yet exhibiting unpredictable behaviors at larger scales. Entropy quantifies the degree of disorder within a system, marking the transition from order to chaos. The second law of thermodynamics states that in an isolated system, entropy tends to increase, leading to a state of equilibrium where all energy becomes uniformly distributed. This principle underpins many natural processes, illustrating a gradual progression toward a state of maximum entropy. In the context of the universe, this gradual increase suggests a relentless movement toward uniformity, characterized by the dispersal of energy and matter. As time progresses, stars will exhaust their nuclear fuel, and galaxies will drift apart, gradually succumbing to the cosmic expansion. The once vibrant interactions that birthed stars and planets will fade, leaving behind a cold, sparse void. In this state, known as heat death, the universe will exist in an unchanging equilibrium. Statistical mechanics not only provides the mathematical framework for understanding these processes, but also offers a glimpse into the ultimate fate of all matter and energy, revealing the quiet inevitability of cosmic stillness. The Boltzmann equation serves as a cornerstone in the study of thermodynamics, bridging the gap between the microstates of individual particles and the macrostates that define the observable properties of a system. This mathematical expression illustrates how the distribution of energy among particles leads to various macroscopic phenomena. It captures the underlying chaos of particle interactions, demonstrating how immense numbers of microstates can result in a singular, stable macrostate. Analyzing this equation reveals a profound truth about the nature of entropy. As systems evolve, they tend to move towards configurations that maximize entropy, signifying a greater number of microstates. This tendency towards disorder reflects a fundamental principle governing all physical processes. In this context, the concept of equilibrium emerges, where the flow of energy ceases and the system reaches a state of maximum entropy. In regions of the universe where gravitational forces are weak, the implications of the Boltzmann equation become increasingly evident. Over vast timescales, matter disperses and energy transitions into forms that contribute to the gradual cooling of the cosmos. As entropy continues to rise, the potential for complex structures diminishes, leading to an ultimate state characterized by uniformity and stillness. This serene end state, wherein no significant thermodynamic processes occur, epitomizes the profound legacy of the Boltzmann equation in understanding the universe's fate. Systems evolve through a complex interplay of energy and entropy, transitioning from ordered configurations to states of increasing disorder. Initially, particles exhibit structured movement, forming coherent patterns that reflect underlying physical laws. Over time, interactions among these particles lead to energy dispersal. This gradual degradation of order illuminates the second law of thermodynamics, which asserts that the overall entropy of an isolated system can never decrease. In this specific context, chaos is not synonymous with randomness. Instead, it represents a natural progression towards equilibrium. Energy becomes increasingly diffuse as particles collide and exchange momentum. These interactions drive the system toward a state where energy is uniformly distributed, a condition indicative of maximum entropy. This evolution is observable in various phenomena, from the cooling of stellar remnants to the gradual fading of radiation from distant galaxies. Observations of cosmic backgrounds reveal this relentless journey toward thermal equilibrium, where temperature differences diminish and the universe's expansion plays a crucial role. The remnants of stars, once vibrant and active, succumb to this slow decay, leaving behind a cold, dark void. Such remnants serve as reminders of a bygone era, illustrating the inevitable transition from dynamic, radiant existence to the stark stillness of heat death. The universe, in its vastness, continues this quiet march toward an ultimate fate defined by infinite entropy and absence of energy gradients. Planets emerge from the gravitational forces at work within a star's protoplanetary disk, a swirling mass of dust and gas. Over countless millennia, these particles coalesce, forming larger bodies that eventually evolve into fully fledged worlds. As they gather mass, their interactions shape the orbits and characteristics of neighboring celestial bodies. This region of space transforms through a series of stages, each defined by intense collisions and gravitational influences. Planetary atmospheres develop under varied conditions, influenced by both the distance from their star and the composition of their building blocks. Volatile compounds may condense into oceans, while geological activity can shape surfaces, giving rise to mountains and valleys. The evolution of these worlds leads to diverse climates and environments, spanning from inhospitable deserts to lush, thriving ecosystems. Over time, these planets may experience cataclysmic events that alter their trajectories and surfaces. The absence of external forces eventually leads to a cessation of geological activity and atmospheric processes. Life, if present, faces extinction as resources dwindle. As entropy increases, the remnants of these planets drift in the cold void, a testament to their once vibrant existence. In this long-term perspective, the evolution of planets reflects both creation and decay, a quiet reminder of the universe's relentless journey towards stillness. The solar system's future unfolds within the framework of stellar evolution, presenting a timeline that stretches across billions of years. The Sun, a middle-aged star, is destined to undergo significant transformations. As it exhausts its hydrogen fuel, it will enter the red giant phase, expanding dramatically. This expansion will eventually engulf the inner planets, including Mercury and Venus, altering their very nature. The remaining planets, including Earth, will experience profound changes as temperatures rise and the environment becomes increasingly inhospitable. Life, as it is known, will face extinction, leaving behind only remnants of its existence. The gradual cooling of the Sun will lead to a slow decline in temperature, marking the transition toward a white dwarf state, where it will shine dimly for countless ages. Surrounding celestial bodies will continue their orbits, influenced by the gravitational interplay among them. Eventually, these objects will collide, merge, or be cast into the vastness of space. The asteroid belt and the distant ice giants will provide clues to this solar evolution, their compositions reflecting ancient histories. In the far future, the solar system will exist as a collection of cold, dark remnants. This desolate expanse will serve as a testament to the slow march toward entropy, where energy dissipates, and silence prevails in the cosmic void, echoing the universe's ultimate fate. Red dwarfs occupy a significant position within the cosmic timeline. These stars, possessing half or less of the Sun's mass, exhibit a remarkably prolonged lifespan, often extending to trillions of years. Their diminutive size and lower temperatures allow for a slow-burning nuclear fusion process, contributing to their stability in the cosmic landscape. Unlike their larger counterparts, red dwarfs do not experience the same explosive fates, such as supernovae, instead fading quietly into white dwarfs over immense spans of time. In this region, countless red dwarfs dot the galactic canvas, providing a steady and unyielding light. Their longevity plays a crucial role in maintaining habitable zones around them, allowing for the possibility of life existing for extended periods. These stars serve as the backbone of galactic structure, their gravitational influence weaving through the nearby interstellar medium. As the universe continues its march toward entropy, the presence of red dwarfs becomes increasingly vital. They outnumber other stellar types and will dominate the cosmos in its final chapters. Their slow evolution ensures a persistent source of energy, enabling potentially habitable worlds to linger amidst the encroaching darkness. This enduring stability contributes to the gradual transformation of galaxies, creating a serene backdrop against the inevitable stillness that follows the heat death of the universe. The Sun's life cycle offers a glimpse into the processes that govern stellar evolution. Approaching the end of its hydrogen-burning phase, it will transition into a red giant approximately 5 billion years from now. This expansion will engulf the inner planets, including Earth, altering the very fabric of the solar system. As it swells, the immense energy output will render Earth uninhabitable, evaporating oceans and stripping away the atmosphere. In its final stages, the Sun will shed its outer layers, creating a planetary nebula. The remnants will leave behind a dense white dwarf, a small but incredibly hot core. This cooling object will gradually fade over billions of years, providing no additional warmth to the surrounding void. Such transformations reflect the inevitable fate that awaits other stars, echoing the broader cosmic narrative. The nearby planets, left without their primary source of energy, will enter a barren state, resembling the cold and lifeless regions found in distant galaxies. Life, as it is known, will cease to exist, leaving only remnants of its former presence. In this vast unfolding expanse, the quiet decay of stellar bodies serves as a reminder of the universe's relentless progression toward cold, lifeless stillness. Each component, from stars to planets, plays a role in this slow, methodical journey towards the ultimate horizon. Time unfolds as an intricate measure across the cosmos, a relentless progression marked by the ticking of celestial phenomena. Light, the fastest entity in the universe, serves as the fundamental unit for this cosmic clock. With distances measured in light years, the movement of galaxies and the pulsations of stars embody the passage of eons, each tick a testament to the vastness and age of the universe. Every tick reveals the intricate relationship between matter and energy. Stars, born from dense clouds of gas, undergo nuclear fusion, illuminating the void. Their life cycles span millions to billions of years, transitioning from vibrant giants to remnants of their former selves, like white dwarfs or neutron stars. In this region, the remnants signal the end of a life cycle, while simultaneously contributing to the birth of new celestial bodies. Galactic collisions, though rare, punctuate this timeline, creating new structures and altering the course of smaller celestial bodies. Each interaction leaves a mark on the fabric of space, shaping the evolutionary trajectory of the universe. The relentless ticking continues, even as entropy rises and energy dissipates. Dark energy accelerates this expansion, pushing galaxies further apart. The eventual fate of Earth hinges on cosmic forces that dictate its long-term stability. As the universe expands, the Sun will exhaust its nuclear fuel, transitioning into a red giant phase. This transformation will engulf the inner planets, including Earth, leading to a stark and inhospitable environment. The surface will vaporize, and any remaining life will be extinguished long before the final inflation takes hold. As the Sun enters its final stage, remnants of the terrestrial world may persist in the form of small, cold bodies, adrift in a dark and empty cosmos. These remnants will continue to cool, losing any semblance of warmth or life. Another scenario involves the gravitational interaction with other celestial bodies. A collision with a large asteroid or comet could significantly alter Earth's trajectory, possibly leading to an early demise. Such an event, while statistically rare, serves as a reminder of the precariousness of planetary existence. In a more distant future, the universe's relentless expansion could render galaxies isolated, with stars flickering out one by one. The cold darkness will pervade, and this ultimate quietude will define the final chapter of cosmic evolution. Life, if it were to exist, would find itself in a fleeting moment, overshadowed by an unyielding stillness. Cosmic rays, high-energy particles originating from distant astronomical phenomena, traverse the vast emptiness of space, carrying with them traces of the universe's history. In the dying cosmos, these particles play a crucial role in understanding the remnants of stellar evolution and the decay of atomic structures over incomprehensibly long timescales. They are omnipresent, penetrating celestial bodies and providing insights into the mechanisms driving supernovae and black holes. In this fading expanse, cosmic rays interact with interstellar gas and dust, ionizing atoms and potentially initiating reactions that could support transient forms of life. Their relentless journey serves as a reminder of the ongoing processes that continue to unfold, even in a universe approaching entropy. The energy contained within these rays, while diminished over eons, still holds significance, illuminating the remnants of long-dead stars and galaxies. As the universe gradually succumbs to the relentless grip of thermal equilibrium, these particles represent both a connection to a vibrant past and a testament to the inevitable silence that follows. Each cosmic ray that enters a celestial environment is a fleeting messenger from epochs long gone, caught in the vast void of existence. In this ultimate horizon, the presence of cosmic rays signifies that even in stillness, remnants of activity persist, echoing through the cosmic quietude. Galactic mergers exemplify a dynamic interplay, where massive structures draw in surrounding matter, reshaping the cosmic landscape. This process unfolds over billions of years, as gravitational forces dominate, pulling smaller galaxies into the embrace of larger counterparts. The collision generates a cascade of celestial phenomena, including bursts of star formation, driven by the compression of gas and dust. As these entities converge, their star systems begin to interact, leading to intricate tidal forces that reshape stellar orbits and initiate complex gravitational interactions. The exchange of material between these bodies results in the accretion of gas and dark matter, contributing to the growth of supermassive black holes at the centers of merging galaxies. This phenomenon plays a critical role in the evolution of galactic structures, with smaller galaxies often consumed or repurposed in the process. The aftermath reveals a new entity, a hybrid of its progenitors, exhibiting characteristics of both. Stellar remnants and gas clouds intertwine, forming a vibrant tapestry of light and energy amidst the cosmic void. Over time, these galaxies find a semblance of equilibrium, settling into a state of relative stability, albeit with the knowledge of their tumultuous origins. In this ongoing cycle, each merger contributes to the grand narrative of cosmic evolution, illustrating the relentless pursuit of balance in an ever-expanding universe. The slow fade of light marks a gradual transition, where stars exhaust their nuclear fuel, illuminating a somber reality. In this region, once vibrant and teeming with energy, stellar bodies shrink into faint remnants of their former selves. Hydrogen, the fundamental fuel, becomes scarce, leading to a cascade of transformations. Helium builds up in the core, igniting fusion reactions that momentarily reignite brilliance. But this phase is ephemeral. As the process continues, these celestial giants swell into red giants, their surfaces expanding and cooling. This expansion engulfs nearby planets, rendering them inhospitable. In the vastness of space, these dying stars emit the last vestiges of light, contributing to the cosmic background glow. Over eons, this light diminishes, a gradual fading echo of energy lost to the universe. Each photon released becomes less potent, swallowed by the vast void. This slow extinction offers a poignant reminder of the impermanence inherent in existence, marking the journey toward the ultimate horizon known as the heat death of the universe. The emergence of brown dwarfs reveals an intriguing aspect of stellar evolution. These objects, often described as failed stars, form when the mass is insufficient to ignite hydrogen fusion in their cores. Their existence highlights the delicate balance between gravitational forces and nuclear reactions. With masses ranging from 13 to 75 times that of Jupiter, they occupy a unique position in the cosmos, bridging the gap between the largest planets and the smallest stars. Brown dwarfs emit very little visible light, primarily radiating in infrared wavelengths. This characteristic allows astronomers to detect them amidst the vast expanse of space. These bodies play a crucial role in understanding the formation processes of both stars and planetary systems. The conditions under which they develop provide insights into the dynamics of molecular clouds and the temperatures required for fusion. The surface temperature of a brown dwarf can range from 1,000 to 2,500 degrees Celsius, cool enough to host various chemical compounds, including water, ammonia, and methane. Over billions of years, they gradually lose heat, transitioning from their hotter states into cooler, more stable configurations. This slow cooling process contributes to the ongoing narrative of the universe's evolution, as each brown dwarf quietly fades into the cosmic backdrop, leaving only traces of its former potential. Degenerate matter emerges as remnants of stellar revolution, a state where matter is compressed to such an extent that it manifests unique properties. In environments characterized by extreme density, such as the cores of white dwarfs or neutron stars, electrons or neutrons are forced into a realm governed by quantum mechanics. This phenomenon results in a peculiar form of matter, where the particles resist further compression due to the Pauli exclusion principle. The implications of degenerate matter extend beyond individual stars, shaping the fates of entire stellar populations. As time advances, these remnants slowly cool, draining energy until they reach a state of thermal equilibrium with their surroundings. In the vast emptiness of space, they become dim, isolated entities, contributing to the cosmic background radiation that permeates the universe. When the universe reaches its ultimate state, it transitions into a phase dominated by black holes and degenerate matter. This environment, characterized by limited energy exchanges, ushers in an era of profound stillness. Eventually, even black holes succumb to Hawking radiation, dissolving into entropy. In this final scenario, matter exists in its most stable form, a quiet testament to the universe's relentless journey towards equilibrium. The remnants of once vibrant stars fade into an unremarkable expanse, leaving behind a haunting silence that echoes through the void. These events, supernovae, serve as crucial mechanisms in the ongoing cycle of cosmic recycling. When massive stars reach the end of their life cycles, they undergo spectacular explosions, dispersing stellar material across their surroundings. This ejected matter enriches the interstellar medium with heavy elements forged in the heart of the star. Elements like carbon, oxygen, and iron, critical for the formation of new celestial bodies, are released into the vastness. The shockwaves generated by these explosions compress nearby gas and dust, triggering new star formation. This process can lead to the birth of clusters of stars, igniting the cycle anew. It is a quiet yet powerful reminder of the interconnectedness of existence within this region of space. Over millions of years, remnants from these stellar deaths contribute to the creation of planets, moons, and, as these new stars shine brightly, they too will one day exhaust their nuclear fuel, repeating the ancient cycle. Each generation is marked by the addition of new elements, gradually building the complexity of the universe. This perpetual transformation underscores the dynamic nature of cosmic evolution, where each end leads to a potential beginning. The vastness of space is not merely an emptiness, it is a fertile ground for rebirth. Shaped by the remnants of stellar giants, the silent universe remains a canvas of profound stillness, where remnants of once vibrant galaxies drift into oblivion. After the heat death, energy disperses and all stars extinguish, leaving behind a chilling darkness. This profound cold engulfs the cosmos as matter becomes increasingly sparse and isolated. Black holes, having consumed their surroundings, become the dominant structures. Over eons, they slowly evaporate through Hawking radiation, an inconspicuous process marking the ultimate decay of mass. The last particles of matter, now scattered across an expansive void, drift aimlessly in the absence of gravitational cohesion. In this realm, cosmic background radiation fades, leaving a mere echo of the universe's once fiery birth. Time itself stretches into an infinite continuum, devoid of events or change, leaving only silence as the defining characteristic. The laws of thermodynamics prevail, dictating an irreversible march toward equilibrium. Every remnant of civilization and celestial wonder succumbs to entropy. Planetary bodies, stripped of their atmospheres, become cold, lifeless husks. This region, once teeming with energy and activity, now harbors only the faintest whispers of existence. Despite this desolation, the universe persists in its own way, even in absence. The heat death manifests as an ultimate horizon where all processes cease and the universe enters its final, quiet chapter. The fate of black holes presents a paradoxical enigma within the context of the heat death. As they gradually evaporate, a process known as Hawking radiation, they emit energy through quantum fluctuations. This energy loss results in a slow diminishment of their mass. The information paradox emerges from the collision between general relativity and quantum mechanics. When a black hole evaporates, the question arises, what becomes of the information contained within the matter that once fell into it? If it is lost forever, it violates the principles of quantum theory, which assert that information cannot be destroyed. Such a contradiction fuels ongoing debates among physicists, as they seek to reconcile these competing frameworks. In the absence of black holes, the universe moves closer to the state defined by the heat death, where entropy reigns supreme. This gradual evaporation of black holes signifies not only the end of these enigmatic structures, but also highlights the fragility of information in a cosmos reaching its ultimate stillness. As the remnants of these celestial objects fade away, the vastness of space becomes increasingly devoid of complexity, inching ever closer to a homogeneous state of existence. Quantum mechanics emerges as a fundamental framework to understand the intricate behaviors of particles at the smallest scales. Within this realm, the notion of reality transforms, challenging conventional perceptions. It introduces a world where particles exist in overlapping states, defying the deterministic nature of classical physics. The principle of superposition illustrates this phenomenon. A particle may inhabit multiple states simultaneously until an observation compels it into a singular outcome. Entanglement further complicates this understanding. Two particles can become intrinsically linked, their states interdependent regardless of the distance separating them. This connection implies a profound interconnectedness that transcends space and time, hinting at a reality that is more intricate than the observable universe suggests. The implications extend beyond mere particles. They beckon questions about the very fabric of existence. The observer effect posits that the act of measurement alters the state of what is being observed, introducing an element of subjectivity that contradicts the objectivity often ascribed to reality. In this region of abstract thought, the concept of time itself becomes fluid, with quantum fluctuations suggesting that past, present, and future may not be as rigidly defined as once believed. These insights invite a contemplation of a universe that is not merely a backdrop for events, but an active participant in the unfolding of reality itself. The inevitability of heat death reshapes perspectives on life and consciousness. As energy disperses and temperatures equilibrate, the capacity for complex structures to arise diminishes, leading to a cosmos devoid of dynamic processes. In this ultimate state, life as it is currently understood would cease to exist. The intricate systems that underpin consciousness would unravel, leaving an expanse characterized by uniformity and stagnation. In this fading company of stars, the implications for existence are profound. The potential for sentience, which relies on fluctuations and exchanges of energy, would be extinguished. Subatomic particles would drift aimlessly across an endless void, devoid of purpose or interaction. This stillness offers a stark contrast to the vibrant ecosystems that currently thrive on planetary bodies, where energy flows and matter cycles through intricate webs of life. Philosophically, the realization of heat death invites reflection on the nature of existence itself. What significance does consciousness hold in a universe destined for entropy? The ephemerality of life gains new meaning when set against the backdrop of an eventual cosmic stillness. Understanding this endpoint encourages a deeper appreciation for the fleeting moments of awareness and complexity found within the current epoch, highlighting the importance of existence in an otherwise indifferent cosmos. The philosophical ramifications of cosmic endings extend far beyond the mere acknowledgement of temporal limits. This concept invites contemplation on the nature of existence itself, raising questions about the significance of life in a universe that, in this context, the pursuit of knowledge and understanding takes on an intrinsic value. It becomes a testament to resilience, as consciousness seeks to grasp the unfathomable vastness of the universe despite its eventual conclusion. This pursuit transforms life into a delicate interplay of hope and curiosity, prompting reflections on the legacy left behind as celestial bodies drift towards stillness. Human endeavors, art, science, and philosophy serve as a counterpoint to the inevitable decay. Each contribution, whether monumental or subtle, echoes through the ages, illuminating the transient beauty of existence. In recognizing the ephemerality of experiences, a profound appreciation emerges for the interconnectedness of all things, fostering a sense of unity amid the cosmos's vast indifference. The ultimate horizon invites not despair, but a tranquil acceptance. It reminds observers that within each fleeting moment lies the potential for profound understanding, enriching the tapestry of consciousness against the backdrop of cosmic inevitability. Information plays a pivotal role in thermodynamics, influencing how energy is stored, transferred, and, in this context, the second law of thermodynamics underscores the inevitability of maximum entropy, where all energy becomes uniformly distributed. When systems reach thermal equilibrium, they exhibit a uniform state characterized by a lack of gradients. This equilibrium represents a profound stillness where no further work can be extracted and all processes cease. The implications extend to the broader universe, where the eventual heat death signifies a state devoid of usable energy. Information becomes static, trapped within the remnants of once active systems. Each particle, stripped of its dynamic purpose, contributes to a cosmic archive, a repository of histories that will never again influence the fabric of reality. Understanding this relationship between information and thermodynamics reveals a serene truth. In the quiet aftermath of cosmic processes, the universe retains a memory, echoing the transient nature of existence. In this closed system, the implications of heat death unfold with precision. Energy, once vibrantly engaged in the complex interactions of stars and galaxies, gradually disperses, succumbing to the relentless pull of entropy. Each fragment of energy, now devoid of organization, drifts aimlessly through the vast expanse. As systems reach equilibrium, temperature differences cease to exist, leading to a state of uniformity where no processes can occur. The concept of a closed system reinforces the inevitability of this fate. It illustrates that no external energy can reinvigorate the cosmos once it reaches this endpoint. The cessation of all thermodynamic activities marks an end not with a bang, but with a whisper, as all matter succumbs to a passive uniform state. These remnants, once vibrant with life and motion, become increasingly isolated, their interactions dwindling. In this stark silence, the universe's history is encapsulated within the fading remnants of stars and galaxies. The remnants of stellar explosions, once harbingers of creation, now serve as mere echoes of what was. This state represents not just an end, but a profound stillness, where the universe's vastness stretches infinitely, unyielding in its quietude. There lies a poignant tranquility in the acceptance of an ultimate horizon, where time itself drifts into obscurity. Understanding the singularity reveals a point of no return, where the fabric of reality collapses into an infinitely dense state. This phenomenon emerges from the equations of general relativity, presenting a region where gravitational forces overwhelm all other influences. In its presence, the known laws of physics cease to function as they once did. Consider this region as a boundary marked by the event horizon, beyond which escape becomes impossible. Approaching this mysterious boundary, an observer would notice that external events become increasingly distant, receding into an unfathomable void. The experience of time itself stretches and distorts, creating a profound disconnect with the outside universe. This isolated existence fosters a sense of finality, as light from the outside world fails to penetrate the oppressive gravity. In this realm, entropy continues to rise, and the universe moves toward a state of maximum disorder. The energy that once fueled stars and galaxies dissipates, leaving behind a cold, dark expanse. The remnants of cosmic structures fade into obscurity, echoing the final chapters of existence. Each particle becomes a mere witness to the inevitable stillness that approaches. Within this harsh reality lies a quiet acceptance of the singularity's role in the cosmic narrative, a reminder of the relentless march toward equilibrium. Cyclic models offer an intriguing alternative to the inevitability of heat death, proposing a universe characterized by perpetual rebirth. These ideas suggest that rather than reaching a final state of uniformity, it may undergo infinite cycles of expansion and contraction. Each cycle begins with a Big Bang, followed by a gradual expansion where galaxies drift apart, only to be drawn together again as gravitational forces reclaim their dominion. In this framework, the end of one cosmic era serves as the catalyst for the next. Each contraction phase culminates in a singularity, a moment of infinite density and temperature before the universe is reborn anew. Such a mechanism challenges the finality associated with heat death, introducing a narrative of continuity rather than closure. This region of theoretical exploration invites questions about the fundamental nature of time and existence. Gravitational waves may play a role in this cyclical unfolding, their presence felt across the vastness, carrying information from one epoch to the next. The vast cosmic voids and dense clusters serve as remnants of previous cycles, echoing the history etched into the fabric of space-time. Through these theories, the universe is portrayed not merely as a singular entity but as a dynamic system, constantly evolving, suggesting a resilience against entropy. Each cycle presents a new opportunity for complexity to arise within the cosmos. The multiverse hypothesis suggests an existence beyond the observable universe, proposing that countless other realms may coexist. These realms could differ in physical laws, constants, and dimensional structures. Speculation surrounding this concept arises from interpretations of quantum mechanics and cosmological observations, hinting at an expansive reality where multiple universes emerge from various cosmic events. In this framework, each universe would represent a unique expression of reality, with its own set of possibilities. This region of thought challenges conventional understanding, representing an intricate web of potential worlds. Here, variations of fundamental forces could yield entirely different phenomena, ranging from the existence of alternative life forms to entirely distinct planetary systems. The implications of the multiverse extend into the philosophical realm as they prompt questions about identity, existence, and the nature of reality itself. The boundaries between universes may be blurred, suggesting that interactions could occur under specific conditions, although these remain purely theoretical. Understanding this concept involves grappling with the very essence of what it means to exist. Each universe, should it exist, offers a glimpse into a broader cosmic narrative, inviting contemplation of the infinite possibilities that lie beyond the limits of current scientific knowledge. Such reflections amplify the wonder surrounding the vastness of existence, revealing a landscape rich with potential. Yet, the role of quantum fluctuations in cosmic evolution reveals intricate layers of reality hidden within the fabric of space-time. These minute variations arising spontaneously lay the groundwork for the development of structure in the universe. As energy fluctuates in the quantum realm, it manifests as temporary particles, influencing gravitational fields and the expansion of space itself. In this region, even the void teems with activity. The energy fluctuations give rise to a spectrum of phenomena, from the formation of galaxies to the birth of stars. They serve as seeds, nurturing the growth of complex systems from seemingly empty space. Over billions of years, these fluctuations contribute to the dynamics of cosmic evolution, shaping the large-scale structure that defines the universe. The interplay of forces, guided by these transient bursts of energy, dictates the fate of celestial bodies. It is within this delicate balance that the potential for life emerges, constrained by the laws of physics, yet liberated by the chaos of quantum behavior. As the universe continues to expand, these fluctuations persist, reminding us of the underlying uncertainty that permeates existence. In contemplating the eventual heat death, the echoes of quantum activity suggest a lingering potential, a quiet reminder of the infinite possibilities that once shaped the cosmos, now drifting toward stillness. Life, in a heat-death universe, presents an intriguing paradox. As temperatures approach absolute zero, the energy fluctuations that underpin biological processes diminish significantly. The inherent chaos of molecular interactions recedes into uniformity, creating an environment where traditional definitions of life struggle to exist. In this cold expanse, hypothetical forms of existence could arise, driven by the last remnants of energy and information. These transient entities might rely on isolated pockets of energy, utilizing minute temperature differentials to sustain themselves. Each interaction would become increasingly rare as the fabric of space-time itself stretches thin, diluting the connections that once fostered complexity. The principles of thermodynamics dictate that all systems, these fleeting configurations, may offer a glimpse into an alternate interpretation of life, one that is not tethered to conventional biological parameters, but instead exists as a manifestation of entropy and order. The potential for such existence invites contemplation about the nature of vitality itself, challenging established notions in both biology and physics. The concept of eternal systems raises profound questions within the realms of astrophysics and cosmology. These structures, capable of enduring beyond the confines of ordinary time, provoke inquiry into their feasibility. This inquiry often begins with the examination of black holes, which possess gravitational forces so intense that even light cannot escape. Within their event horizons, time behaves differently, hinting at realms where conventional understandings of existence may falter. Stellar remnants, such as white dwarfs and neutron stars, exemplify the enduring nature of certain celestial bodies. These compact entities carry the remnants of once vibrant stars, maintaining stability through intricate balances of pressure and gravity. Their lifespans extend far beyond the typical evolutionary timelines of their progenitors, allowing for contemplation of survival in a universe that dark energy adds another layer of complexity to this discussion. It drives the accelerated expansion of the universe, suggesting that distant galaxies will recede beyond observable limits. The implications of this expansion suggest a future where celestial bodies become isolated, leading to a stark stillness across vast reaches of space. Such considerations reveal the delicate interplay between creation and dissolution, prompting further exploration into the possibility of systems that transcend the inevitable decline towards uniformity, providing a foundation for understanding existence in a seemingly indifferent cosmos. An exploration of stillness invites contemplation on existence itself, offering insights into the nature of time and the experience of consciousness. In this ever-expanding universe, stillness manifests as a paradox, embodying both emptiness and potentiality. It raises philosophical inquiries about the essence of reality, leading to the question of whether true stillness can exist amidst relentless change. Examining the voids between celestial bodies reveals a canvas where time ceases to hold the same significance. These vast expanses become arenas for philosophical reflection, emphasizing the contrast between dynamic creation and the eventual quietude of decay. The notion of stillness challenges traditional understandings of movement, suggesting that moments of serenity may offer clarity amid the chaos of existence. Such philosophical explorations also delve into the relationship between consciousness and the cosmos. As entities capable of reflection, there is a unique position held in relation to the surrounding stillness. This awareness invites consideration of life's impermanence and the search for meaning within the confines of a universe destined for entropy. In these contemplations, the concept of stillness becomes a profound teacher, revealing that even in the face of inevitable decline, there exists a space for thought, introspection, and understanding. This perspective reshapes the narrative of existence, illuminating the quiet beauty found within the cosmic cycle. Artificial intelligence plays a pivotal role in deciphering the complexities of cosmic futures. It processes vast amounts of astronomical data, enabling researchers to identify patterns that would otherwise remain unseen. This technology allows for simulations of various cosmic phenomena, offering insights into the potential outcomes of stellar evolution and galactic interactions. Through deep learning algorithms, it analyzes light curves from distant stars, facilitating the detection of exoplanets and contributing to our understanding of planetary systems. These systems provide clues about the conditions that may lead to life in the universe. The integration of AI into astrophysics has transformed how scientists approach questions about the universe's fate, revealing probabilities and scenarios that extend far beyond human calculation. In this endeavor, AI systems can refine our models of dark matter and dark energy, elements that fundamentally shape the structure of the cosmos. The collaboration between human ingenuity and machine learning enhances our grasp of gravitational waves, allowing the exploration of phenomena previously deemed unobservable. Such advancements might eventually contribute to predicting events that occur over billions of years, like the potential collision of galaxies or the gradual dimming of stars. The continuous evolution of these technologies promises to deepen our understanding of the universe, bringing clarity to the intricate pathways that lie ahead. Cultural perspectives on cosmic endings weave a rich framework of interpretations and beliefs surrounding the eventual fate of the universe. Diverse civilizations have imagined the finality of existence through various lenses, often influenced by their philosophical and spiritual narratives. These interpretations provide insight into how humanity perceives its place within the vast cosmos. In some traditions, the concept of cyclical time predominates, suggesting that the universe undergoes infinite cycles of creation and destruction. This perspective offers a sense of continuity and renewal, where endings are merely preludes to new beginnings. Philosophers and astronomers alike have explored these themes, contemplating the implications of cosmic rebirth. Contrastingly, linear interpretations of time embrace the notion of a singular, definitive end. Such views often resonate with existential inquiry, prompting reflection on mortality and the transient nature of all existence. This understanding can evoke a sense of urgency, urging individuals to seek meaning within their finite lives as they confront the inevitability of cosmic stillness. Ancient texts and modern literature alike depict these endings, imbuing them with significance that transcends mere physical phenomena. The heat death, a state of maximum entropy, serves as a backdrop for dialogues on energy, life, and the universe's ultimate fate, encapsulating humanity's quest for understanding amid the vast stillness of eternity. Human consciousness emerges as a remarkable phenomenon amid the expansive silence of impending heat death. It represents a unique intersection of awareness and existence, capable of reflecting on the implications of entropy and cosmic decay. This cognitive capacity allows for introspection and the questioning of reality, bridging the gap between ephemeral human experience and the inexorable march toward an entropic end. In this context, the mind grapples with the paradox of being a fleeting observer in a universe governed by relentless thermodynamic principles. Rather than succumbing to despair, it finds meaning in the transient nature of moments and relationships. The pursuit of knowledge becomes an act of defiance against the inevitable, a way to assert significance even as the cosmos drifts toward uniformity. Philosophical inquiries arise, pondering the essence of existence when faced with a future devoid of energy gradients. They explore the value of creativity, love, and memory, all of which contribute to the richness of experience. This realm of thought shapes cultural narratives that transcend generations, fostering a collective consciousness that seeks to preserve understanding in the face of cosmic stillness. In a universe steadily approaching equilibrium, the role of consciousness transforms from mere survival to a profound quest for meaning, highlighting the intricate interplay between awareness and the vast, unyielding fabric of time. The trajectory toward heat death serves as a critical focal point in cosmology and physics, pushing the boundaries of current understanding. This state, characterized by maximum entropy, raises fundamental questions about the ultimate fate of the universe. Theoretical models suggest a gradual decline in star formation and the eventual cooling of stellar remnants. These changes lead to a dark, quiet universe where energy is uniformly distributed and complex structures dissolve into simplicity. In this scenario, the laws of thermodynamics dictate the inevitable fate of matter and energy. As stars exhaust their nuclear fuel, remnants collapse into neutron stars or black holes, while galaxies drift apart into the void. The fabric of space-time itself may experience a transformation as gravitational forces weaken and the very essence of space may become indistinct. This quiet yet profound shift invites exploration into the nature of existence. It poses philosophical inquiries about the significance of life in a fast-approaching stillness. Concepts such as information retention and black hole thermodynamics challenge traditional views, sparking debates among physicists. In the face of this cosmic inevitability, the pursuit of knowledge remains a testament to the resilience of inquiry. Each discovery contributes to an understanding of the universe's intricate mechanisms, even as it moves toward its ultimate, tranquil conclusion. Energy harvesting emerges as a crucial aspect in the quest for sustainability within this vast, changing cosmos. Technologies designed to capture ambient energy from the environment offer insight into how civilizations might adapt to shifting energy paradigms. Solar panels, for instance, convert sunlight into usable electricity, demonstrating a fundamental principle of harnessing natural resources. Wind energy, with its turbines rotating gracefully, illustrates another method of extracting power from atmospheric movements. Each mechanism reflects an understanding of energy flow, revealing the potential to transform transient forces into stable power sources. This region of study not only addresses immediate energy needs, but also paves the way for long-term solutions in a universe where resources may become increasingly scarce. Thermal energy harvesting further exemplifies this innovative approach, capturing heat from the surroundings and converting it to electricity. These advancements signify a shift towards efficiency, emphasizing the importance of sustainable practices in an ever-evolving landscape. In contemplating these developments, the interconnectedness of energy systems reveals a pathway to resilience. This focus on renewable sources can lead to a reduced ecological footprint, aligning humanity's needs with the rhythmic cycles of nature. As the universe continues its quiet march towards stillness, energy harvesting stands as a testament to adaptability, echoing the enduring quest for balance amidst change. The ethical implications of a heat-death universe invite contemplation on the essence of existence. In a realm where energy becomes scarce, the very fabric of life faces unprecedented challenges. Resource allocation, once a simple matter of abundance, transforms into a complex framework of moral decisions. Individuals and societies must navigate the consequences of a dwindling energy supply, questioning the equity of distribution and the prioritization of survival. This scenario prompts reflections on the value of consciousness. The pursuit of knowledge, art, and culture may diminish as the universe cools. The fading vibrancy of these aspects raises inquiries about their worth in an environment devoid of warmth. It suggests a re-evaluation of priorities, urging societies to consider what constitutes a meaningful existence when faced with existential exhaustion. Interpersonal relationships become paramount in this context, as the bonds forged between individuals might serve as a vital source of warmth and connection. In a stagnant cosmos, collaboration could emerge as a fundamental necessity, fostering resilience amidst scarcity. The journey toward establishing ethical frameworks may reveal a deeper understanding of humanity's role in the universe, emphasizing stewardship over exploitation. Each choice carries weight, echoing through the fabric of existence. The unfolding narrative of life in a heat-death universe becomes a profound exploration of purpose within the vast expanse of time and space. Forceful scenarios about existence beyond heat-death reveal intriguing possibilities. In this scenario, life might adapt to the chilling embrace of an ever-expanding cosmos. Organisms could evolve to harness the faintest remnants of energy, drawing sustenance from the lingering radiation of subatomic particles. These entities would likely develop unique biochemical pathways, enabling them to thrive in near absolute zero temperatures. This region of existence would be marked by an intricate interplay of dark energy and gravity, possibly leading to the formation of isolated pockets where remnants of life could be sustained. Intelligent systems might emerge, capable of contemplating their own survival against the backdrop of entropy and decay. Such beings could employ advanced technology to manipulate their environment, perhaps creating artificial conditions that mimic the warmth of a bygone era. The concept of memory in this desolate landscape would take on new meaning. Echoes of a vibrant past may persist through encoded information, preserved within the structures of what remains. These echoes could serve as a reminder of what once flourished, spurring the continued quest for understanding and existence. The fading company of stars would provide a haunting yet beautiful reminder of the cosmos journey, illuminating the path for those who seek to grasp the essence of life in the silence that follows. Technological advancements in astrophysical research have emerged as a beacon of enlightenment in the vastness of the universe. Instruments designed to observe cosmic phenomena have reached unprecedented levels of sensitivity, allowing scientists to detect faint signals that once eluded even the most robust telescopes. These innovations, including powerful space-based observatories and ground-based arrays, delve deep into the expansive realms of space, capturing data that unravels the complexities of celestial bodies and their interactions. Observations of distant galaxies reveal insights into their formation and evolution, shedding light on the processes that govern their existence. The development of adaptive optics has mitigated the distortions caused by Earth's atmosphere, enabling clearer views of the night sky. This clarity assists in decoding the behavior of exoplanets, where atmospheres are analyzed for signs of habitability. Advanced computational models simulate cosmic events with remarkable precision, predicting phenomena such as gravitational waves and black hole mergers. These simulations serve as a virtual laboratory, providing a deeper understanding of the fundamental forces that shape the universe. The fusion of artificial intelligence with astrophysical research aids in processing vast amounts of data, identifying patterns and anomalies that guide future explorations. In this era of discovery, the tools of science continue to expand, revealing the intricacies of the cosmos and the quiet elegance that underpins its existence. The art of visualization embodies a critical aspect of cosmic studies, transforming complex numerical data into comprehensible images that convey the enormity of the universe. Through advanced algorithms, vast datasets are translated into visual formats, illuminating the hidden structures of galaxies and the distribution of dark matter. Such representations breathe life into abstract concepts, allowing researchers to grasp the scale and dynamics of celestial phenomena. Scale and dynamics of celestial phenomena. In this context, three-dimensional modeling plays a vital role, providing a spatial understanding of cosmic formations. These models reveal the intricate relationships between various elements, such as stars, gas, and gravitational forces, elucidating their interactions in a vast, ever-evolving landscape. The interplay of light, color, and shadow in these visualizations enhances the perception of depth, offering a glimpse into realms that remain otherwise inaccessible. The depiction of cosmic events, such as supernovae or the merging of black holes, further enriches scientific narratives. These illustrations serve not only as educational tools, but also as a means to inspire curiosity. As researchers delve deeper into the intricacies of the universe, the visual representations become invaluable, fostering a dialogue between observation and interpretation. This integration of visualization within cosmic studies underscores the importance of clarity and comprehension, bridging the gap between complex theories and universal understanding. The influence of religion on cosmic perspectives has shaped humanity's understanding of existence for millennia. Various belief systems offer unique interpretations of the cosmos, often framing it within a narrative of creation, purpose, and destiny. This regional viewpoint manifests in the reverence for celestial bodies, as they are often viewed as manifestations of divine presence or guidance. The interplay between spirituality and astronomy is palpable in ancient cultures, where celestial events were frequently interpreted as omens or messages from the divine. Temples and observatories, constructed with precise alignments to the heavens, demonstrate a deep-seated connection between terrestrial life and cosmic phenomena. These structures often serve dual purposes, functioning as sites for worship while also facilitating astronomical observations. In contemporary discussions, faith continues to influence how individuals relate to concepts such as the heat death of the universe. This eventual end state, characterized by maximum entropy and uniformity, poses existential questions that intersect with theological beliefs about the afterlife and the nature of the soul. Philosophical inquiries arise as scholars consider the implications of such a fate, pondering the intersection of science and spirituality. This dialogue enriches the understanding of cosmic phenomena, fostering a broader contemplation of existence within an ever-expanding universe. A cultural reflection emerges as science fiction influences the public's perception of cosmic realities. This genre often acts as a bridge, connecting complex scientific concepts to the broader imagination. In countless narratives, it explores themes of entropy, the ultimate fate of the universe, and the inevitability of heat death. These stories introduce abstract ideas through tangible characters and compelling plots, making the intricacies of astrophysics more accessible. Imagining distant galaxies and the slow march toward thermal equilibrium becomes a means for society to grapple with existential questions. This creative framework allows for an emotional connection to the scientific discourse, prompting discussions about humanity's place in the cosmos. Speculative scenarios present potential futures where civilizations confront the limitations of energy sources and the consequences of cosmic expansion. Works of fiction often depict advanced technologies that manipulate space-time or harness energy from stars, reflecting a blend of hope and trepidation. While grounded in reality, these narratives explore the ethical implications of such advancements, leading to a deeper understanding of technological impact on society. As public interest in the universe grows, the dialogue between science and fiction continues to evolve. It encourages critical thinking and fosters a sense of wonder, shaping how society perceives its own trajectory in a vast, indifferent universe. Imagining the future of cosmology may reveal profound insights into the universe's fate. As it continues to expand, the fabric of space-time undergoes significant transformations. Observations indicate that galaxies are receding from each other, their velocities increasing as a consequence of dark energy. This region of the cosmos is characterized by a gradual cooling, with distant celestial bodies becoming increasingly isolated within the vast emptiness. The implications of this expansion become clearer when considering the long-term evolution of stars. Stellar life cycles are finite, with massive stars. In this context, theoretical models predict a future dominated by entropy. The balance of energy will tip unfavorably, leading to a state where all thermodynamic processes cease. This quiet annihilation of activity suggests a universe that becomes increasingly homogeneous and devoid of complexity. The interconnectedness of all cosmic phenomena becomes evident as disparate elements converge toward a singular fate. Galaxies, stars, and cosmic distances interact within a vast framework, governed by the fundamental laws of physics. This region, rich with dark matter and energy, exerts influence on the behavior of celestial bodies, binding them in an intricate web of gravitational forces. Every stellar birth and death contributes to this cosmic narrative, shaping the evolution of matter and energy across epochs. Supernovae release vast quantities of elements into the interstellar medium, seeding future generations of stars and planetary systems. Each cycle of creation and destruction underscores an underlying unity, revealing that what exists is merely a transient expression of more profound, immutable laws. In the cold stretches of space, remnants linger from ancient collisions and mergers, echoing the history of the universe. These ruins, silent witnesses to the passage of time, tell stories of formation and dissolution, reinforcing the notion that every phenomenon exists in relation to others. The cosmic web weaves together galaxies, clusters, and filaments, forming a colossal structure permeating the void. The gradual approach toward heat death renders these connections increasingly subtle, As energy dissipates and interactions diminish, the pursuit of knowledge embodies a fundamental aspect of the human experience. Within the vastness of the cosmos, the quest for understanding extends beyond mere curiosity, acting as a beacon guiding generations of thinkers. This endeavor fosters a profound connection to the universe, allowing individuals to explore the mechanics behind celestial phenomena and the intricacies of existence itself. In laboratories and observatories, scientists meticulously gather data, seeking patterns and explanations amidst the darkness. Each discovery contributes to a larger framework of understanding, illuminating the nature of reality. From the smallest particles to the grandest structures, each element plays a role in a unified narrative of the cosmos. Philosophical inquiries into existence often arise alongside scientific advancements, prompting reflections on humanity's place within this expansive realm. These musings intertwine with empirical findings, resulting in a rich dialogue that shapes both scientific thought and cultural identity. Engaging with the cosmos invites contemplation on the impermanence of life and the inevitable fate awaiting all matter. The ongoing exploration of the heat death symbolizes not just an end, but a transformation, urging humanity to embrace inquiry and wonder. Through this lens, the human experience is framed as an ongoing journey, revealing the beauty of understanding against the backdrop of an ever-evolving universe. Acceptance emerges as a profound response to the inevitability of heat death. This phenomenon signifies the gradual decline of energy differentials, leading to an eventual state of uniformity across the cosmos. With time, stars will extinguish, galaxies will drift apart, and the once vibrant universe will reach a profound stillness. It becomes essential to reflect on this transition, recognizing the transient nature of existence and the fleeting moments of brilliance that punctuate its history. In the context of this vast expanse, the remnants of stellar life serve as poignant reminders of creation and destruction. The remnants of stars, now reduced to dust and gas, hint at the cyclical nature of matter and energy. These remnants may eventually coalesce, forming new structures in a universe that remains relentlessly indifferent to its own fate. This acceptance fosters a deeper understanding of our place within this intricate web of cosmic processes. It imparts a sense of humility, encouraging contemplation of life's impermanence and the interconnectedness of all entities. The final state is not merely an end, but rather a transition into a new form of existence, a stillness that reflects the essence of the universe itself. The ultimate horizon signifies a boundary where chaos recedes into equilibrium, marking the transition from vibrant activity to serene stillness. Within this expanse, all cosmic phenomena gradually subside, yielding to a profound tranquility. Stars extinguish, galaxies drift apart, and the remnants of once thriving celestial bodies fade into a dim, homogeneous backdrop. This transition embodies an inevitable process, driven by the relentless march of entropy. Energy disperses, leaving behind a universe where temperature gradients equalize, and all matter coalesces into a state devoid of motion. In this region, interactions cease, and the dynamic forces that once animated the cosmos dissolve into inertia. Particles find themselves in constant, random motion, yet without meaningful interactions. Their presence becomes a mere whisper in the vastness. The remnants of structures, once teeming with life and energy, dissolve into an unremarkable expanse of uniformity. The stillness at the ultimate horizon invites contemplation of existence beyond dynamism. It serves as a reminder of the cyclical nature of creation and destruction, emphasizing the transient nature of all things. Within this quietude lies a profound understanding of the universe's fate, a destination that beckons with the promise of peace amid the remnants of cosmic turmoil. time itself becomes irrelevant, marking the end of the observable and the beginning of an existence based solely on stillness.